We are recording this, as you can hear, so thank you again for joining and welcome. I hope you're all keeping well. We did have over 100 people register from 8 different countries across Europe, the USA, Canada and China, and 7 decades of alumni as well. So welcome to all of you. I'd like to start by saying a huge thank you to all of you who have supported our student support funds in recent weeks. That is going to make a huge difference and we're incredibly grateful. So thank you so much. A few pieces of housekeeping. So as you've heard, we are recording this session and the video will be available through our website. Your videos are off and your microphones are muted. So if you have any questions as we go, you can ask via the question and answer box, which should be at the bottom of your screen. We'll try and get through as many of these as possible. Blake will try and keep an eye on them as he speaks, and I'll also try and sum up at the end. If we do have any major internet issues in that unlikely event, then we will try and reconnect and keep it going. If there is a huge problem, then we will reschedule. So that's all the housekeeping out the way, and I am delighted to now welcome one of our alumni, Dr. Blake Sherwin. He read maths and physics at Trinity Hall from 2004 to 2008. I first saw him speak at the Science Museum in London for the launch of the university's Stephen Hawking programme, Stephen Hawking also being an alumnus of Trinity Hall. And Blake is a theoretical and observational cosmologist who works as a university lecturer in the Department of Applied Maths and Theoretical Physics. He did his PhD at Princeton, was a fellow at Berkeley before returning to Cambridge in 2017. So his talk today is entitled Seeing the Beginning, the Cosmic Microwave Background and What It Can Tell Us About Our Universe. So I will hand over to Blake, who will be sharing his screen.
All right. All right, let's see if this works. Hopefully you can all see my screen now. Shell, everything looking good? All right, excellent. Right, so thank you so much for attending this webinar. I'm going to be talking about the cosmic microwave background, the afterglow of the hot Big Bang, and what it can tell us about our universe. So here's sort of a brief outline of this webinar. Let me start off by just reminding you of some things that I'm sure most of you already know about the expanding universe and why it strongly suggests that the universe began in a hot Big Bang. So first, just a quick reminder of where we are, right? Our sun is a pretty typical star in the Milky Way galaxy, which has 300 billion stars, very similar to our sun. But the Milky Way galaxy is, of course, not the only galaxy out there in the universe. We've now observed in modern astronomical telescopes and surveys many hundreds of billions of galaxies. So I can just show you some actual data. So these are real images of galaxies that we've observed with the Sloan Digital Sky Survey. So these are images taken by a telescope. And so these are real images and real positions, and someone's assembled them into a video that you can sort of fly through. And each of these galaxies that you see here has hundreds of billions of stars in it, just like our sun. And most of them have planets, just like our solar system. Now, for a long time, people thought that the universe was kind of static and unchanging. But all of these enormous number of galaxies we've seen, we now know that they're moving away from us. And this was first discovered by Edwin Hubble in the 1920s. So he discovered that not only is the universe not static and the galaxies are not stationary, but in fact, they're all running away from our positions. They're all moving away from us. And in fact, he discovered this somewhat strange law where the further away the galaxy is from us, the faster it's running away. Now, why does this arise? Why is it that galaxies are all running away from us? Are we sort of particularly repulsive and horrible that everything needs to get away from us? No, our current understanding is that the reason all galaxies are running away is because space itself is expanding with time. So let me I tried to illustrate this with kind of a cartoon. In the cartoon, each of these sort of blue blobs represents a galaxy. And so you can imagine us being this galaxy here, but it doesn't really matter. And now, as time passes, as space itself expands, the distances between our galaxy and every other galaxy increase with time. But it's not like our galaxy is special, right? It's just that all galaxies are moving away from, every galaxy is moving away from every other galaxy. And the further the galaxy is away, the more space there is in between us and that galaxy, and so the faster it runs away. So that's the explanation for why galaxies are running away from us. It's because space itself is expanding. Now, this was a surprising discovery in its own right. You know, the fact that the universe isn't static and unchanging, but it's a dynamical object on its own right. But it was also a really surprising discovery because of what it suggests. Because you could imagine running this kind of diagram or a video in reverse. If you keep running it in reverse, and you imagine just sort of extrapolating, you could think about the fact that in an early time, all the galaxies and all the matter could have been really, really, really close together, arbitrarily close. I can run it in reverse. And so when everything is really, really close together, it's really dense. And usually when you compress things, they become hotter. So this expansion suggests that the universe used to be much, much denser and much, much hotter than it is today. And in fact, that it had a beginning in an incredibly hot, incredibly dense state called the Big Bang. Now, when this idea was sort of proposed, it wasn't universally accepted. Some people still, really didn't like the idea that the universe had a beginning in this sort of hot Big Bang. But in fact, there was a big fight in Cambridge between the sort of group that thought there was a Big Bang and people like Fred Hoyle, who proposed that maybe the universe is expanding, but it's been expanding forever, and there's always matter that gets created. And so there was one major piece of evidence that definitively established that the hot Big Bang happened. And that's the main subject of my talk. And this sort of piece of evidence that demonstrates that the hot Big Bang happened is the cosmic microwave background. And that's what I want to talk about next. Are there any questions, though, so far? Feel free to just ask in the Q&A. Let's see. All right, I think no questions so far, but feel free to ask. All right. So how can you prove that the hot Big Bang happened? What is a prediction you can make? Well, in this hot Big Bang model, the very early universe is really different from the way it is today. It's incredibly hot, incredibly dense. And it's so hot that it's almost like the interior of the sun. It's a state of matter called a plasma. And in this incredibly hot and incredibly dense state, the heat is such that even atoms can't really hold together. Right? So it's so hot that protons and electrons are separated. And they're sort of bouncing around this plasma along with light, along with the sort of glowing light or photons. So it's an incredibly dense and hot plasma, and it's also opaque, so the light just keeps bouncing around. But, so that's in this hot Big Bang picture, that's the early universe. It's an incredibly hot, opaque plasma. But over time, what you would predict is that the universe expands and it cools as it expands. And so eventually, after a little bit of time, after a few 100,000 years, you would expect that the protons and electrons have cooled down enough that they can form atoms. And now suddenly, when atoms can form, the universe becomes transparent. And the afterglow from this really, really hot plasma, which is almost like a sea of fire, like the interior of the sun, this afterglow then gets released and can travel through the universe. So this was maybe a lot of information. Let me show you a video kind of illustrating that. So you'll see the early universe, where it's a plasma of protons, electrons, and light, and then the light can escape as the universe cools. So here, the light is these blue blobs. This is obviously kind of a cartoon. It's bouncing around off the protons and electrons. It's really, really hot, really dense early universe. Eventually, it cools enough with the expansion that the universe becomes transparent and the light gets released. And so this is, a photon. This is the light, the afterglow from the Big Bang, and it can travel through the universe for billions and billions of years until eventually, today, it reaches our telescopes. All right, so to summarize that picture, in the hot Big Bang model, the early universe is very different. It's almost like a sea of fire. It's incredibly hot and incredibly dense, but that afterglow light should eventually be released and stream through the universe for billions of years until it reaches us. And this prediction, this afterglow light from the hot early universe, is called the cosmic microwave background, or CMB. Now, there's another way of thinking about this, which I think is actually really interesting. Another way of understanding why this hot Big Bang theory predicts the CMB. And it has to do with the fact that cosmologists, we're actually able to see the past. So this is something that I think a lot of people don't realize, that we don't have to speculate about what happened in the past. We can actually see the past. So, and the reason for this is that light travels at a finite speed. So if I'm looking at an object that's on the other side of the room, the light's taken a few nanoseconds to reach my eyes. And so I'm seeing that object a few nanoseconds in the past, not really a big difference. But if I look at something that's really far away, for example, I look at a star that's, say 1 million light years away, then the light's been traveling for so long that I see that star as it was 1 million years in the past. But now I could take this argument further. I could say, well, what if I look out all the way into the darkness, as far as I can possibly see? Eventually, I should look so far back, so far out, that I should see so far back in time that eventually I should run into, effectively, the primordial fireball from the Big Bang itself. So that's another way of understanding why, when I look out into the night sky, I should be able to see this cosmic microwave background afterglow light. All right, so just to reiterate this, the sort of hot Big Bang theory makes a very clear prediction. When we look into the night sky, we should see the leftover light from the primordial fireball, from the hot Big Bang in the sky. So there's one question. Let me just pause here. If the universe is expanding, how is it possible for galaxies to collide? Well, sometimes, galaxies, it's a little bit simplified that they just move with the expansion of the universe. Sometimes they have their own little velocities and they can then end up colliding. So, but we're looking at the sort of bigger picture where they're all expanding. All right, so the Big Bang theory makes a clear prediction. We should be able to see light from the primordial fireball whenever we look out into the night sky. But you may have noticed that if you go out at night and you look into the sky, you do not see a burning sea of fire. You don't see a fireball in the sky unless something has gone horribly wrong, right? So most of the sky at night is dark. And why is that? Have we just disproven that there's a hot Big Bang? So just to explain why I'm showing this lozenge, I'm going to show these kinds of plots a lot. Basically, what I'm imagining is I'm taking the globe, the night sky, which is all around us, and I'm unfurling it and putting it on the page. Okay, so why don't I see this? This is a prediction of the hot Big Bang. Why don't I see the cosmic microwave background afterglow? Well, the answer is that you need to account for the fact that the light has been stretched. The wavelength of the light has been stretched by the expansion of the universe. So it starts off a visible glow, just like from the sun, but then the wavelength of the light gets stretched by the expansion. And so what you predict is that it should be, the color should be microwave wavelength now. It should be sort of microwave light rather than visible light. But what you can do is you can build microwave eyes, effectively, microwave telescopes. And if you then look into the night sky, then you really should be able to see this radiation, this afterglow light from the hot Big Bang, the CMB. And this is indeed what was discovered by these sort of FBI agent-looking guys here, Arno Penzias and Bob Wilson, in 1968. In fact, this is one of the great stories in science, though. They made this discovery, the first discovery of this prediction, the Big Bang afterglow, the CMB. They made it by accident. Well, by accident and by being fantastic experimentalists who really wanted their experiment to work. So the sort of story is that Penzias and Wilson had built this Holmdel-Horn antenna, a microwave telescope, for totally different reasons. They were trying to study communications equipment and also do some astronomy. But even though they were really good experimentalists, they just couldn't get their telescope to work the way it should. So for some reason, they always had this extra, annoying signal that they didn't understand. They thought their instrument, their telescope, was malfunctioning. But they did a huge amount of work. They checked everything. They checked their detectors and their refrigeration and all kinds of aspects of their experiment. And they just couldn't figure it out. And there are all these stories that show just how desperate they were and how they just didn't understand what was going wrong with their telescope, right? So eventually they thought, well, the only thing that it could be is that we have a bunch of pigeons that have been nesting in the telescope. And they've been leaving their droppings, which are kind of warm and they radiate a little bit of heat. Maybe that's what's going on. And so there's this, you can see in a museum, there's the sort of the trap that they use to try to get rid of these pigeons. And one of them climbed in and scrubbed the telescope, and they still couldn't get rid of it. And so, it really illustrates just how desperate they were to figure out what was going on. Why was their microwave telescope not working? Why was it finding this extra signal that they weren't expecting? And there's actually kind of a fun, I never heard this story until I saw a talk by Bob Wilson in person. And then I looked into this. It turns out there's a sort of, they got so desperate that it didn't just end with the trap. At some point, one of them bought a shotgun and just killed all the pigeons because they were so frustrated. But eventually, after a long time, they were lucky and they had a phone call. They were on the phone with a group of sort of Princeton cosmology theorists, sort of Bob Dickey and Jim Peebles, who had sort of made this prediction that if the hot Big Bang model is correct, you should be able to see this afterglow, the cosmic microwave background. And then they realized what they had found wasn't a problem. It wasn't something wrong with their experiment. It was actually, the afterglow of the hot Big Bang. And indeed, the proof that the hot Big Bang is what happened in the early universe. All right, of course, you want to do a little bit more work. More work was required to show that what they found was indeed the cosmic microwave background, or CMB. And so an additional very precise prediction you can make is that what kind of radiation, what kind of light you expect the CMB to be, right? You expect it to be the glow of a really, really, of a hot object, which you call black body radiation. And you can actually predict roughly sort of what temperature it should have, and you can predict what the color is basically of the radiation. Or for those of you who are scientists, basically you can predict the frequency spectrum, how bright it is as a function of frequency. So this is sort of a modern measurement showing in black a theoretical prediction. This is what you predict if the CMB is indeed coming from the hot, glowing early universe, the hot Big Bang, and the measurements are shown in these boxes. Right, so I think the measurement of the CMB and just proving that it has the right color, the right frequency spectrum, is really a stunning confirmation that indeed the universe began in a hot Big Bang. All right, Let me pause now for questions. Are there any questions about how, the Big Bang picture inevitably predicts that you can see this afterglow, the cosmic microwave background, or CMB, and therefore the discovery of the CMB was really the smoking gun that proved that the hot Big Bang happened, because basically we can see it. All right, let me just see if there are any questions. Right, so there are actually quite a few questions. Yeah, let's see. So there's one question: is there any theory that the expansion of the universe will stop and reverse under the influence of gravity? Yeah, so that what will happen in the future depends on what's in the universe, right? And so what it's made out of. And if you have a lot of normal matter, then yes, that could happen. But we now believe that due to what's in the universe, that won't happen. It'll continue to expand and get bigger and bigger. So that was one question. Another question is, let's see, why does the wavelength expand with the universe? Yeah, that's kind of that's a good question, and to explain that in real detail, maybe you'd have to understand the physics a bit better. But yeah, let's see. I mean, effectively, you can just think that all lengths kind of get bigger that are participating in the expansion, and so the same is true for the wavelength. But yeah, I don't know if I can give a more intuitive explanation than that. All right. I can take more questions at the end as well. I'm just going to pick up a few as I go. Okay, so again, glowing hot early universe predicts radiation that we can see, and we have seen it. And it has, basically we can see the afterglow of the Big Bang. It confirms that that's what has to have happened. Now let me talk about some more recent work. What else aside from confirming that the hot Big Bang happened, what else have we learned about the universe from patterns in this CMB radiation? All right, let me explain a little bit what I mean by patterns. And the question that motivates this is, you could ask, well, the universe today isn't uniform. Is the CMB, the afterglow of the early universe, is it uniform? Is it the same brightness no matter where I look in the sky? Again, so this is sort of this lozenge is the night sky. And basically, to first approximation, it is uniform, right? To first approximation. So, from a first look, if I look here, or I look somewhere else in the night sky, it has the same brightness. But I can build better and better experiments. I can increase the contrast by a factor of 1,000. It turns out it's still uniform. But in 1991, we had built such a good experiment that it could see variations in the brightness at the level and a part in 100,000. And when you look with such a sensitive experiment that's able to sort of turn up the contrast by so much, what you see is this beautiful picture here. So this is showing that there are actually variations in the brightness of this cosmic microwave background, variations in the afterglow of the hot Big Bang. So in some directions where, someone chose a color scale in such a way, in some directions where it's red, the CMB is a little bit brighter than average. But in other directions where it's sort of shown in a blue color scale, it's a little bit less bright than average. Okay, so there's these tiny variations in how bright the CMB is, depending on where you look in the sky. There are fluctuations in the brightness. All right, but that was in 1991. Technology has progressed a lot, going from this first discovery with COBE that also won the Nobel Prize to the WMAP satellite, and now to the Planck satellite, in which a lot of Cambridge scientists were also involved. And so the Planck satellite made the current best picture of the fluctuations in the CMB. In other words, of the variations and the patterns in the brightness of the CMB. So this is our current best picture of how bright the CMB is a function of where you look in the sky. Right? So it's gotten incredibly detailed now. So again, where this is the color scale is chosen such that where it's colored red, that's a direction where the CMB radiation is a little bit brighter than average. And where it's blue, that's a direction in the sky in which the CMB is a little bit less bright than average. And these variations are apart in 100,000, something like that. And I just think this is a beautiful picture, right? And it's worth just looking at this and thinking about how amazing this is, right? We are looking at this light that's been traveling for such a long time that we are literally seeing a picture of the past. And so this image, this CMB afterglow image, is basically a picture of the universe as it looked nearly 14 billion years ago. So this is, in some sense, actually a picture of the Big Bang fireball. So we're not speculating about the past always. We can actually see it. All right, and again, reminding you what happened. Early universe was really hot. The glow was released and travels the universe, reaches our telescopes. And by looking around at how bright the CMB is in different directions, we're able to make a map of the night sky in microwaves. And this is what it looks like around the Earth. And that's that picture I showed you. All right, let's see if there are any questions. This might be a good place to stop. There are lots of questions. Right. Let's see. Yeah, so let me just try to answer one question. Which is, so is the CMB afterglow visible in any direction? And why is it not emanating from the site of the Big Bang and directional? So one thing, with apologies for my barking dog, basically every galaxy could see the CMB, right? It's not coming from one point. The Big Bang didn't come from one point. The Big Bang just describes the fact that everywhere the densities were incredibly, incredibly high. So this light is released from everywhere in every direction, right? And so every observer, no matter where they are in the universe, will, when they look out, they'll be able to see this afterglow, right? So the Big Bang didn't happen at one point. If you think about galaxies coming close together, it just describes the sort of time when everything was arbitrarily close together. All right, more questions later. All right, so we've seen these fluctuations in the CMB, in the brightness. Why are they there? Okay, what does this mean? Why are there these differences? Why is it a little bit brighter if I look in that direction compared to this other direction? Well, the very simplified explanation is that this is reflecting the fact that in the early universe, some regions have just a little bit more matter than other regions. Okay, so if I look at the density of matter, if I'm looking somewhere where it's brighter, that reflects the fact that there's a little bit more matter in that location. Okay, if there's more matter, then it's a little bit denser and it's a little bit hotter and it emits more. Okay, so the variations in brightness of the CMB that I can see in this picture reflect the fact that there's small differences in how much stuff there is in different regions of the universe that I'm seeing. And this is incredibly important for understanding how our universe today evolved. And the reason that's true is because basically the CMB is kind of the baby picture of the universe. It shows the way the universe was almost at the very beginning. And so the initial state of the universe, as we see in the CMB, is not perfectly uniform. There's small, it's almost uniform, but there's small variations in how much matter there is from point to point. And so it allows us to understand how the structures we see today form. So what I mean by the structures, I mean things like planets and stars and galaxies. Where did they come from? Well, you can see their origin in the CMB, basically, right? So if I have a region that's red, that means there's a region with more matter. What happens if I wait billions of years? A region with more matter has more gravity than average, so it pulls in even more matter, and then it has more gravity, and you get this kind of runaway collapsing and clumping that leads, one of these spots where there's a tiny bit more stuff than average to over time form stars and galaxies. And in fact, what we can do is we can even simulate this. You can take basically the variations in the matter that we see in the CMB, the fact that it's almost uniform, but not quite uniform, and just let gravity do its thing. And you get this kind of clumping and collapsing where, things will, a cloud of gas will collapse and, stars will turn on and galaxies will form. So I'll just show you an example of one of these simulations. You start off almost uniform, but with small variations, and you let gravity work, and it sort of enhances these differences and causes the formation of planets and stars and galaxies, etc. Okay? So, the CMB is really important because it allows us to see the baby picture of the universe. It allows us to understand how stars and galaxies evolved from the way the universe was right at the very beginning. All right, let's see. Let me ask one more question here. Let's see. Yeah, there's one question. Could these fluctuations be used to predict the shape of the universe? I'll come to that right now. Okay, so basically the first reason looking at these patterns in the CMB is important because it allows us to understand, where stars and galaxies come from. Well, you could say we haven't totally answered the question because I haven't explained where do these small differences in density come from in the first place, and I'll talk about that at the end of my lecture. But there's a second reason I want to briefly mention of why the CMB has been so important for cosmology. It's because, now that we see it, we've observed it so well, and we understand it very well, we can actually sort of use it as a tool to learn about what's in the universe and, how old the universe is, how big the universe is. We can just understand all the properties of the universe. Let me give you an example of how this works. For example, say you want to determine the size of the observable universe, right? How far you can see. Well, what you can calculate and what we understand is basically the intrinsic size of these CMB patterns. And to figure out how big the universe is, you can go look at the CMB patterns that you observe. And if they appear really big in the sky, that means they were emitted very close by. And so the CMB is pretty close and the observable universe is quite small. On the other hand, if the patterns appear very small, then the CMB was emitted from very far away and the observable universe is very large. So this is just an example of how you can use the CMB as a tool to understand the properties of the universe. And so using the CMB as a tool, by studying these patterns, we've been able to determine things at really incredible accuracy. For example, we now know that the age of the universe is 13.798 plus or minus 0.037 billion years old. We also now know at incredible accuracy what the universe is made of, what its composition is. It turns out from the CMB, but also from, it's not just the CMB, from many other observations, we know that only 4.6% of the energy of the universe, only 4.6% of the universe is made of atoms, which is kind of the stuff, the normal stuff that we're all very familiar with. And it turns out, I won't have time to discuss this in detail, but I'm happy to take questions on it, that the other 95% of the universe is made up of dark matter, 24%, which is a strange form of invisible matter, And more than 70% of the universe is made up of something even stranger, a form of energy that accelerates the universe apart and actually implies that it won't ever recollapse. It'll just keep getting bigger and bigger and bigger. So from the CMB and from other observations, I think on the one hand, you really should take away that we have learned an enormous amount already about the universe. We've confirmed that the hot Big Bang happened. We also understand how stars and planets and galaxies evolved just under gravity from small initial variations in the density that we see in the CMB. We've also precisely determined what the universe is made of. But, you don't have to take this optimistic perspective. And if you look at, a tabloid newspaper that reports on cosmology and talks about dark matter and dark energy, you will see a very different perspective taken, especially if you read the comment section, which is never a good idea. So here's an article about dark matter and dark energy in the Daily Express. And you can read these sort of comments. And obviously I don't totally agree with them, but I think that some of these comments do make a good point, which is that we don't really understand things all that well. And even though we've learned a huge amount from the CMB and other cosmological observations, in some sense, we've figured out precisely how little we understand of the universe. So there are really big open questions that we still have yet to answer. Let me just pause for questions, and then I'll move on to talking about the sort of cutting edge research and trying to answer some of these big remaining questions. Yeah, sorry, by the way, sorry I'm not able to answer all the questions. There have been actually a lot of questions, and I think hopefully we'll have time at the end of the talk to go more systematically through all the questions. I'm just picking one or two at each time. Let's see. So there's some questions about the evolution of the CMB, like, do the patterns change? What happens over time? Well, the first thing that happens, if you imagine you looked at the CMB in a billion years or a few billion years, what would it look like? Well, first of all, it would be the light would be stretched out further, so it would be even. It would be in an even redder color, so it would be a different color. But the patterns would be a little bit different. They wouldn't change that much typically, so you pretty much have to wait a billion years, a few hundred million years or so until the patterns appreciably change, just because of the size of the variations in the matter that you're probing. They're quite big, and so it takes a while to look past them. All right, so good. Let me just move on. All right, please continue to ask questions. And hopefully we'll get to some of them at the end that weren't answered so far. Okay, so what don't we still understand, right? We've just basically figured out a huge amount from the CMB and other observations, but there are big questions we don't understand yet. And so these questions are, for example, what is dark matter? What is dark energy? I won't talk much about these questions, but another big question is, what exactly happened at the very beginning? That's a big open question. And what I mean by that, let me try to be a little more precise. On the one hand, what blew the universe up in the first place? But perhaps, I think equally interesting is what set up these tiny fluctuations in density that are really the seeds from which stars and galaxies grew, and that we see in the patterns of the CMB. So I explained that all stars and galaxies grow through gravity from what we see in the CMB, these tiny variations. But where do these tiny variations in how much matter there is come from in the first place? Now, surprisingly, we don't know this for sure. This is still somewhat speculative stuff. But we have a pretty good theory for what happened in the very beginning. and basically at the Big Bang or in the Big Bang itself. And this theory is called the theory of cosmic inflation. And effectively, it's a proposal that there's a kind of substance which has various technical properties that I'm not going to explain in detail, sort of called an inflaton substance, and it was designed to really blow the universe up. So theorists came up with this. They wanted to see if you could blow the universe up really fast and make it big and flat. And so, it works, right? So at least in theory, you have the substance. What it does is accelerates the universe apart and blows it up by a huge factor in a very short amount of time. But what I think is really amazing is that by accident, this wasn't intended in the development of this theory, it provides an explanation for where these sort of seeds from which all galaxies and stars grew came from. So it explains, almost unintentionally, it explained where these differences, these fluctuations in the density came from that we see in the CMB. And it's a really, I think, a really cool idea. The idea is that the origin of these tiny variations in the very beginning of the universe in density come about because this huge expansion and inflation blows up the strange microscopic world that's governed by quantum mechanics to be macroscopic, to be the size of the universe. All right? So inflation explains where the variations in density comes from by blowing up the weird microscopic world and making it big. All right, let me try to explain what I mean by the weird microscopic world. This is all a little bit advanced and technical, so don't worry if you don't fully understand this. So what do I mean by the strange microscopic world? So if you look on really, really tiny scales, on subatomic scales, the laws of physics are not the ones that we're familiar with. What happens is governed by the rules of quantum mechanics. And in quantum mechanics, the key point is that there's always some randomness that you just can't get around. And so because of this, even empty space is never really empty. So this is a simulation of the density of empty space. And because of this unavoidable randomness on really, really, really tiny scales, what you see is these quantum fluctuations, random fluctuations in the density. You see just blobs of matter popping in and out of existence randomly. Now, this all seems very weird, and indeed we're not at all familiar with this kind of really subatomic regime, but it's pretty well established that this is the way quantum mechanics works. And so normally we don't notice this. We don't notice these tiny microscopic random fluctuations, and we don't encounter them. But what inflation does is it's a period of huge expansion, and this expansion blows up one of these random fluctuations and makes it enormous and macroscopic and real. So the way, the really cool idea is that inflation blows up a random subatomic, microscopic quantum fluctuation, makes it real and macroscopic, and makes it into a real variation in how much matter there is. It makes it into a real dense blob of matter that we see in the CMB. And this is then the seed from which over time a galaxy, for example, will grow. So, I mean, I really think this is a very profound, maybe even somewhat disturbing idea, right? That it implies that if this inflation theory is correct, we exist, our star exists, our galaxy exists because at our point, at our position, 14 billion years ago, there was a subatomic random fluctuation in the density that then got blown up, would be visible in the CMB, and then gravity causes it to collapse and our star to go on. So, I think it's really interesting. It's also a little bit disturbing that if there's a random subatomic fluctuation that's responsible for everything, if this is correct. Okay, so this all sounded somewhat speculative. Now, how can you test this experimentally? This all maybe sounds a bit made up and speculative, but actually we can make lots of predictions that we can test because these random quantum fluctuations are very special. They have certain They have very specific properties, and we can compare whether the fluctuations we see in the CMB match the properties you expect from sort of quantum fluctuation origin of these variations in density. And so, for example, you can, even though it's random, you can predict the probability distribution. You can predict, that it has to be exactly sort of a bell curve distribution. You can predict many other things about the sort of statistics of these patterns. And so far, everything, there's been several tests, they've all passed successfully. So, they're all consistent with this sort of random quantum fluctuation origin for these variations in density. But there's still one prediction from this inflation idea that I think is really a great idea that we have not yet seen. And this is what we're looking for now. So the one prediction of this inflation theory that we haven't seen so far is that it predicts a certain very characteristic pattern in the CMB that we haven't seen yet. And basically, it's kind of a swirly pattern in the polarization of the CMB called B-mode polarization. And so we really want to be able to find this characteristic B-mode polarization pattern. First of all, because if we can find this pattern, we would confirm that inflation is the right theory for what happened at the beginning of the universe. But also, in more detail, if you can measure the strength of how strong these swirly patterns are, you can pin down what kind of inflation model is responsible. So I'm not going to explain this plot in detail. I'm just going to show these are different models for the physics of inflation. They all give you different predictions for what the strength of the signal should be, but they all predict basically that it should be there. So we really want to find these characteristic B-mode swirly patterns in the microwave background, because if we can find them, we would prove that inflation is the right explanation for what happened sort of in the beginning of the universe itself. And that's what my collaborators and I are working on, both on the theory side and on the analysis side, on the experiment side, with several new telescopes. For example, here's the Atacama Cosmology Telescope. You can see here, there's a variety of they're typically ground-based, large CMB telescopes, such as this one, or arrays of such telescopes with large and small components. So right now, we're trying to find these patterns, and if we can find them, we will have confirmed that inflation is the right explanation. All right, so to wrap up a little bit, I hope I've conveyed that we really have learned a huge amount from the CMB about how the universe evolved from its initial conditions to today. We've confirmed that the hot Big Bang happened, but they're really, in some sense, we've just learned quite how little we understand. And they're really big open questions that we still want to answer. For example, what is dark matter? What is dark energy? And what I talked about in more detail, what exactly happened at the very beginning and set up the seeds from which all structure grew? Was it inflation or something else? One thing that I think is certain is that the CMB will continue to give us lots of insight into the beginning of the universe, its composition, its evolution, and its ultimate fate. So thanks very much.
Wonderful. Thank you, Blake. Fascinating talk. And there's been lots of questions coming in. So thank you to all of you that are listening. What I'll try and do, I'm very grateful to Blake for trying to read them all as we're going through, but I'll try and couple them, some of them together in themes. And towards the start, there were a few questions about wavelength and why wavelength expands with the universe. And is the longer wavelength with the expansion of the universe like the Doppler effect with sound? I don't know if you can comment on that, Blake.
Yeah, you could potentially understand it as sort of a Doppler effect. I've seen it explained in that way, that you could think of, if everything is moving away from you, then, just like an ambulance passes you by, then the frequency goes down. And if a galaxy is moving away or the CMB is moving away, then the frequency would go down as well. So if that is, yeah, you can explain it like that. in some sense, there's some technical issues why it's a little better to think about it as just everything being stretched out. But yes, that's also a good explanation.
Wonderful. And thinking right at the start, a couple of the questions: why is CMB not just at the edge of the universe rather than throughout, if it came from a singularity and is expanding? And also, if all matter in the universe was in a tiny volume at the start, how come it wasn't a black hole? So going right back to the very beginning.
Right. So the CMB is everywhere. It's just that the CMB that we are seeing right now has traveled for basically the age of the universe, and it's only reaching us now. So we are sort of seeing a surface, right? It's almost like we're seeing a surface, and it's a surface in time, right? It's exactly how far away light was released that's just reaching us now. But if we're somewhere else, we would see the CMB coming from anywhere else. So it's a little bit hard to visualize this. I need to draw lots of things, but the CMB is everywhere. And if I were in a different galaxy, I would also see the CMB. It would just be coming from a slightly different location.
Brilliant. There were a few questions as well when you had the slide about the understanding cosmic evolution and with the kind of the image and the map, saying the map shows a variation of the intensity. Is there any variation of the characteristic frequency? And is the image pseudo-random in intensity?
Right. Basically, it's just a variation in the temperature. It's a variation in intensity, but there's also a change in the color that all just looks like a change in temperature. So it's so yes, there is some variation in the frequency and the color, but it's all completely described by just being a little bit hotter or colder. So there's not that much more information. It's basically, you can just imagine it as variations in brightness. In fact, that's one of the ways that we separate. There's another question I saw. How do we separate the CMB from other stuff that might be in the way, right? The CMB basically just has this black body frequency spectrum, whereas if you have, galactic dust or stars or something else, they have very different frequency spectra. And so this kind of characteristic color allows you to separate the CMB from other things that might be in the way.
Wonderful. A couple more questions as well, more detailed. Something about dark matter, and I saw on the last few slides that you think there's still a lot unanswered there. But a question saying, what fermions or bosons would dark matter be made from or carried by? Can we answer that question?
Yeah, I think this is still an open question. There are various proposals. So yeah, basically, what you need to get a dark matter candidate particle. So we basically know all the properties dark matter has. It's something that's invisible, but it's invisible and it can't experience large forces, but it has to, we know it's there because of its gravity, right? We know that, there's a substance that's invisible, but has a lot of gravity and pulls on everything with gravity. So yeah, what kind of particles could it be? So we don't know, but there are a few possibilities are, for example, people proposed these things called sort of supersymmetric particles. So it could be that it's a supersymmetric particle, although the LHC has maybe disfavored this a bit. I think probably right now, the most promising dark matter candidates are probably things called axions. They're sort of scalar fields. Not, spin zero boson, if you want to be technical. Yeah, so I think, but we don't know. I think there's lots of investigations going on, both on the cosmology side, but also in the lab, trying to figure out exactly what kind of particle is the dark matter, but that's still an open question.
Brilliant. And someone who is trying to go back to their, I think their Natsky days and their degree, saying they get why hot original radiation gets frequency shifted by inflation, but why do we see it now?
Well, there's light sort of whizzing around, right? And it's just the light that you see, so whenever you look out at any time in the universe, you're always going to see some light that's left over. It's just that depending on when you look, that light will have traveled the later you look, the further away will be the source of this radiation, effectively. This is a little bit hard to visualize, but there's always radiation whizzing around, and yeah, so you will always be able to see it. And just the longer you wait, the further away it will have been emitted from, if that makes any sense. But yeah, I think I'd need to draw some diagrams for this to make a lot more sense.
And then the final few questions are all kind of looking forwards. So someone asked, how long until the expansion makes itself known within our galaxy? And our final question that's come in, could another quantum fluctuation also undergo inflation and form another universe? And what would govern the interactions between these two universes?
Let's see. Right, so there are, I think this is sort of still an open question and things like that. I mean, there are various ideas about, could you have sort of different inflating patches, and could they collide? And people have studied this in detail and looked for it. In fact, that you could maybe even see this in the CMB. So yes, this could happen, and you could see sort of different inflating patches colliding, and you'd see weird rings in the CMB. And so this is something that people look into, but we have no evidence for that so far.
And sort of what further progress do you think you can expect from more precise observations from new telescopes?
Right. So I think, Johnny Tang asked a question about getting more, how things have improved with higher resolution. So yeah, the improvements on the technical side have come from building telescopes with higher resolution, but also building telescopes that are more sensitive, in other words, have lower noise. And in particular, the thing that's probably new now and that will drive progress in the next decade is that we're really starting to study the polarization, right? So far we've really gotten a lot of our information from the variations in brightness or the temperature of the CMB. But now the sort of new frontier is really low noise, high precision studies of the CMB polarization. And that's something that's barely been exploited, and that we're only just starting to get the information out from there.
Wonderful. Well, I know it's coming to 6:30. There's one final question that's come in. Are you sure dark matter is another form of matter and not an issue with our theories on gravity?
Yeah, so this is a question that I think people have thought about a fair bit, and there are ideas such as MOND, et cetera, where where you think you could imagine it. People have thought, well, if all the evidence for dark matter comes from gravity, couldn't it be something wrong with gravity? But I think at this point, that's really hard. That's very hard to have work in detail. I mean, part of the reason is the CMB is so precise. We have these incredibly precise measurements, and it works really well with just a particle, right? And it's very, very hard to explain with just some modification of gravity, right? Our measurements have gotten so precise that these are sub% level precision measurements. And so you can't make these really major tweaks anymore without breaking lots of things. The model is very well constrained, and it's very hard to get away with this. I mean, there's lots of observations. It's not just the CMB either. There's a ton of observations that sort of imply that it's probably nothing wrong with gravity. For example, there's this famous bullet cluster observations where sort of two galaxy clusters came together. And so the visible matter, these galaxies merged, these galaxy clusters merged, and the visible matter collided and shocked. But the dark matter, we know, just sailed right through. So it really seems to be a different kind of substance from all the normal atomic matter that we see. And it would be very hard to explain some weird issue with gravity that caused, some to mimic that. So I think people have considered it, but it's very hard to make sort of modifications of gravity work in the same way.
Wonderful, thank you. Well, I hope we've got through most of the questions. Apologies if we didn't get through to answering yours. We've had a huge amount of the questions come in, which is fascinating, and again shows such an interesting talk that you've given, Blake. So thank you so much to you. Thank you to all our attendees for joining us on our first webinar. Apologies to those of you who had difficulties with the technology at the start. We do have a recording and we will send that out when it is available, hopefully in the next few days. So if you did miss the very beginning, then there will be a recording available. So thank you once again to Blake, a virtual round of applause, and thank you to all of you for joining. We will be having more virtual events in September. So I hope you all keep well and have a wonderful summer. Thank you so much.
Thanks. Bye, everyone.